And we're back. It's been a little while, I know. I think that's sort of my canonical introduction at this point, since it's always been a little while. And I think my canonical outro is I'll always make more. But anyway, I know it's been a little while since we've talked heavy duty quantum sort of stuff, especially a long while since we talked about quantum machine learning. I'll talk about that maybe a little more at the end. But for now, I'm just going to cut straight to the chase and get into talking about trotterization today, which is a topic I learn about for these videos, and hopefully the next one you'll see some discussion of the Ising model in here. Hopefully the next one will be heavy duty Ising model, of course focused on quantum computing. But yeah, I always feel like I talk too much at the beginning of these intros, so I'm talking, whatever, cutting straight to the chase now. If you notice a difference in my writing or on the screen text, just to note, in the long run it should be better, because previously I was using my mouse with a low DPI setting to draw on the screen, but now I actually got a little writing pad or drawing pad that, really common with like digital artists. Not that I'm a digital artist, but that should hopefully in the long run really improve my handwriting, how fast and neat I can do things. But I just got it, and this is my first time ever using it, so you might have to bear with me a little bit at the beginning, or these first few times that I'm using it before I really get the hang of it. Yeah, so without any further ado, let's talk about trotterization. So when we're talking about this trotterization, I should go over and start at the very beginning. You can see, I don't know if you can see my little cursor, if that only shows up for me, but I will now write the word trotterization. Maybe this is going to be less helpful because you can see that my handwriting is naturally not very good. But I'll practice, and this should get better. Okay, so let's start at the very beginning. And when I say the very beginning, I of course mean the Schrodinger equation. So we have our Schrodinger equation. Might go a little slow just to make sure. It's interesting as I write, knowing exactly where my cursor is as I'm looking at all these screens. I'm looking at this screen, I'm looking down at the screen on my little writing pad. It's just very new to me. So anyway, we have our time-dependent Schrodinger equation, for those of you, of course, familiar with it. If you are not familiar with it, then I advise you to familiarize yourself with it, because a discussion, that's so sideways, of it is out of scope of this video. I was thinking actually of doing sort of an intro to quantum mechanics video, or series really, because I really want to restructure and reinforce my basics and make sure I have everything down. I'm not really sure if I'm the most qualified to do that. I'll let it slip here that during my college career, I never got an A in a quantum physics class. So do with that information as you will. Maybe take my lectures with a grain of salt then. But anyway, getting back to the time-dependent Schrodinger equation we have, very familiar for anyone working. Oh, this is interesting. I haven't written much. Very familiar for anyone working in any physics field. We have, oh, interesting. Sorry, I'm making a lot of weird sounds as I'm getting used to it. So we have our time dependence here, the derivative with respect to time. And then we have our position dependence, where here this is the Laplacian, which is of course equal to, and the Cartesian coordinates. Oh, that's a terrible partial derivative. Oh my god. You can see it's going to take me a little bit to get better with it. Yeah, see, I'm not quite good at lining these up. Okay, I'll stop talking about it though. So that's in sort of the 3D coordinates. But anyway, and this is our potential energy. This is sort of the kinetic energy time dependence. But anyway, that's not important. What's important is that if we solve this, and the canonical way to solve this is to separate our wave function, which is a function of position and time, into a function of position and a function of time. This is what's called separation of variables. Which is, I did not take differential equations for a very long time, so maybe that's why I did poorly in quantum, but this is a common technique to solve differential equations, is to simply say, okay, our solution that we're looking for, right, this wave function is simply two functions multiplied together. So we can separate it out. Long story short, I won't go through all of this, it's very established. We get 1 over f of t. And here I'm just writing the derivative sign because we only have, this is a function of one variable, time, where E is the energy, of course, right here. So you can see, you can solve this out, or you cannot, and just trust me when I say that the answer is an exponential. We see that f of t equals e to the negative I energy times time over h bar. Okay, well, now you're probably wondering, oh, when you're talking about Trotterization, why the hell are you talking about all this Schrodinger equation stuff? And that will become clear shortly. But first, I just want to make a little note. This is really common because you'll notice this disappears whenever, a lot of times if you have to do, expectation value, of your little, x operator. And you're going to have to do some integral, right? And then you have the star x. This is really common for any intro class, right? Well, these are going to cancel because you'll have e to the I e t over h bar and e to the negative I e t over h bar. And these are just going to, this is going to equal out to 0, and it's going to become 1. So it's nice to see that the solution is of that form because it's very much cancels out in a lot of these applications. So anyway, should get back into the Schrodinger equation. We can rewrite this a bit easier. The original Schrodinger equation above in the following form, where we have our I h bar, the partial with respect to t of our function. Where now I'm switching to this Dirac notation. And then we have over here the same position kinetic and potential energy operator, which we're just going to write as our Hamiltonian. So now we can just see this is the same form, of course, as above. It's just in a different format. So if we go ahead and solve this out, we can see that our wave function at time t is equal to, of course, we need an initial condition for our to solve a differential equation like this. So we have our unitary operator of time. This is, of course, every operator is going to be unitary that I know of. And maybe since it's basically probability preserving, I don't know what a non-unitary operator would look like. And so we can see, of course, following the trajectory above, that we have this e to the negative I. Instead of energy now, we just have our Hamiltonian. Of course, the minimum eigenvalue of this will be our energy, our ground state energy. So you can see now we can do the classic physicist move and say h bar equals 1, and now we just have e to the negative I h bar t. So now that's an important equation right there. You will probably have seen this a lot, even if you just skimmed quantum computing papers. This is a lot of introduction before I even talked about Trotterization or quantum computers before. This is the first time we're talking about either of those things. So now let's talk about it a little bit more. We have our thing here, our equation, e to the negative I h bar t, which is the time evolution operator, as it's commonly called. Now let's suppose, well, I have a quantum computer. It represents states in an exponentially scaling manner. This seems like a good idea. It's a naturally quantum device. Feynman said, let's make quantum computers to simulate quantum mechanics. I want to simulate this. All right. So our problem now, the problem that we're trying to solve here with Trotterization on quantum computers is how to do time evolution of a Hamiltonian. And this is how we do it, right? We operate, okay? Now let's say, okay, our wave function at state 0 is a quantum computer. It's at some quantum state. I want to evolve it using a unitary operator, which is, of course, fair because that's, how we do quantum computing is through unitary operators. So you say, I want e to the negative I h t as a quantum operator, or sorry, a quantum computer. There's a little pad on this. I'm not sure if I'm supposed to leave it on. Let me try taking this off real quick. Oh, am I supposed to flip? No way. What is this? Sorry, there's a little sticky thing on. Oh, maybe I do it this way. Okay, sorry, my writing pad is confusing me a little bit. Maybe that's what I do. Let's try this a little bit. Maybe this will make it easier. Let me try just taking this off. Sorry. I feel like I shouldn't. I'm just going to leave it on the way it was for now. And then I'll hold it with my other hand and we will see how this works. Okay, so I want this on a quantum computer. Well, how am I supposed to do that? Of course, I can just calculate the matrix and you can be like, and this is easy. I can do circ.matrixGate, and I just solved it. Problem solved. We did it. We solved quantum simulation. The problem is, of course, that doesn't work. You can do the matrix exponential, but one, you don't want to have to do that on a classical computer because the whole point is to do Hamiltonians that are hard to simulate on classical computers. And two, that's not how any real quantum computer will ever work. So the question becomes, how do we actually represent this on a quantum computer? Now it's worth noting that, let me scroll down a little, that this Hamiltonian is rarely just one term. Often we'll see it represented as a sum of terms. So we have some summation, however many terms there are, I'll just write as n here, that the Hamiltonian is written as. So we want an approximation, or ideally an exact decomposition of this exponential into our friendly quantum computer compatible gates. So let's just assume for now that this is some Pauli operators. This is a fair assumption because Pauli operators are universal, and if you have some constant here, I'll just say lambda I, you can make any Hamiltonian from this. So without loss of generality, we can say that. So now let's get into it. Well, first, we'll note what an important theorem or limit or whatever you want to call it is. And I'm not entirely sure on who everything is named after. You'll see a lot of like Trotterization, Lie Trotter, Suzuki Trotter, all this stuff thrown around. So I'm trying to keep it sort of straight, but if I mess something up, you can correct me in the comments, or the names aren't as important as the ideas. I'll just put it that way. So we have the Lie product formula. I'm pretty sure that's what this one's called. We have this saying that if we have our sum here, where we have I to n of our Hamiltonian terms, and then we have t. You can move it to either side, it doesn't matter. This is equal to the limit as n goes to infinity of the product here, where this is product, not sum, of e, we'll do I to n, e to the negative I, h of I, t. Sorry, this should be I shouldn't have used both ends, but I'll just do n here. So that little n is the limit n. So as this goes to infinity, this becomes true. Of course, we cannot do infinite gates on any quantum or classical computers, but this is the theorem, or the formula, I guess, that we're going to be working with. As a fun exercise, you can prove it. I actually don't know how fun that is. I've never done that, and I probably never will. But if you want to do it, you can go for it. So now that we have that equation, let's talk about how do we do this on a quantum computer. So this part's easy. If we have some term, e to the negative I z times 0.5, for example, say that's our time, we can do this on a quantum computer. We know how to exponentiate Pauli's. You can look up all the gory details about it, but just know that's possible, and it often involves, unfortunately, a lot of C0 gates. You often see, I believe it's e to negative I z. This would be, someone can correct me, I may be wrong on this. I believe this is going to be a C0 RZ C0. And then the more you have, right, if it was ZZZ, it would be C0 C0 RZ C0 C0. But someone can correct me if I'm misremembering that. But anyway, the important thing is that for any given term, we can, of course, do this. And doing products of these is very easy because let's suppose we have our circuit. Interesting. I'm scrolling down again. Suppose we have our circuit for, this term, and we want to multiply it. So we have e negative I z z. We have e negative I x x. Well, we can just do, on our zero state, we just do this operation first on our circuit, then we just do this one, and then we're good to go. Easy peasy. So this product formalization is very nice. So let's start off with, okay, we're trying to approximate this limit. We're never going to get there. It's just impossible. We don't have infinite compute, unfortunately. We live in a finite world. So let's do the simplest approximation. Let's do n equals 1. So we have our approximation e to the negative I sum of h. I'm going to drop everything here. I meant like the i's and the n's here. Time equals product e to the negative I h t. Now the error associated here with this approximation scales quadratically with both the number of terms in the Hamiltonian, so this was n, and the time. So for very small time steps, this is very good, right? Because as this, if this is 0.5, then our error scale is 0.25025. Oh my God, that's embarrassing that I can't just do I can't do that in my head instantly, but it's really late. That's my excuse, is that it's late. 0.5, 0.5, 2.1. So that's my excuse. But yes, it is 0.25. It's I don't know why I put a 0 there. Okay, but anyway, you can see that this scales favorably for low time. But if we wanted to repeat it, we could simply say, okay, we're going to approximate it. I should really say, arrows here, e to the negative I h t over r, repeat it r times, and this will scale O of n squared t squared still, but we divide it by r. So the bigger r is, of course, the smaller the error is. And this is the basic idea right here of Trotterization. We break our Hamiltonian up into products instead of sums, and then we do these products repeated for potentially many layers, and then we get our results that we care about. So that's basically Trotterization in a nutshell. This idea right here of converting our time evolution Hamiltonian to a quantum computer friendly set of products is Trotterization. Now, what is Suzuki Trotterization? Well, that's basically just a better approximation by canceling out some things. So basically, instead of just having the I sum of ht, now instead of just having this one term in here, we have our product for, and here I'm going to actually write them out because for a reason you'll see shortly, e to negative I h t over 2r. And this time the reason you'll see is we have I equals n to 0. So this is the reverse. I negative h t over 2r to the r. And this scaling has m to the third, t to the third over r squared. So that's what's called the second order. And the order here is basically the, sorry, I keep adjusting my writing, but I forget that my hand is very close to my writing pad, so it messes up my other sort of attempts to use the computer. So the order is sort of the approximation level. The higher order you have, basically, so this is second order, maybe I should write that second. The higher order you have, the more terms that you'll have in here. There's a general formula, which I'm going to write out from, if you remember from our penny lane videos, this was actually mentioned here. The alternative for this quantum simulation stuff is called qubitization, but we won't talk about that here. So I'm just going to write out this equation. Let me scroll down a little. So this is the general recursive definition. I'll link the papers, of course, below, where we have u to so we have u to the k, where k mod 2 equals 0, t equals, then we have u to the k minus 2, sk t squared, u to the k minus 2, 1 minus 4sk, and I'll talk about what sk is here, t, and then we have this repeated u to the k minus 2 sk t squared. So this sk is just a term defined as 4 minus 4 to the 1 over k minus 1 inverted. And so this just comes from the paper. I won't get into explaining it, but it's basically just a recursive definition for improving the quality of approximations. So once again here, now we have an order parameter, order, which is what this k is. And then we have our repetitions, which is r, both of which can be scaled. So that's Suzuki Trotter. So now we have ideas for how to do this on a quantum computer. Let's actually look at some code. But the one last thing I want to do before looking at that code is talk about the model we're going to be using. I implemented a few different things, but the one we're going to be looking at is the transverse field Ising. Very common. So our Hamiltonian is described by the following. This is very common. Let me scroll down. So the Hamiltonian, the TFI, transverse field Ising, is defined as negative, and here you'll sometimes see a parameter j, but I just dropped it because it's doesn't really matter. I even work with just, so we have our zi plus 1, and then we have our minus g xi. So there's a lot to talk about here in terms of Ising models, but I'm not super familiar with them, and they will probably be the topic of another video. But basically, these are, of course, the interacting terms. This is the background term. And as you change this parameter, you can see very interesting things happen, phase changes, localization, lots of interesting things that are hopefully to be discussed later. But basically, this is our Hamiltonian. So we want to construct e to the negative I, well, I guess plus I, because we have a negative sign out front, I sum of j z. You get the zz minus gx. So this is our Hamiltonian times t, and this is our goal. All right, so now let's actually look at doing this in code. So let me just put this stylus down and move this, I guess, into my lap. All right, move my mouse. My desk is very crowded now. So now let's go over to the tab where I have my Jupyter Notebook open. And you can see I have chosen to do a Jupyter Notebook to save the figures. I'm thinking about moving more and more to Jupyter Notebooks rather than just Python files. I felt like Python files are useful for some people, but Jupyter Notebooks are useful for everyone, so they keep results very easily, so why not use them? So of course we have our standard imports here, TensorFlow-Quantum, circ. We actually don't need this import. I never ended up using that. And then we define our Hamiltonians as polysums over here. There's some examples here, but we're focusing on the transverse field Ising here, which we define basically as this is the negative z's. We just drop this j and assume it's 1. Then we have the g's right here. We also just put 1s in for those, but in theory, you could change that. We have an example where we generate the expectation value, a function where you generate the expectation value. We given some circuits and symbols. Remember, these are unparametrized circuits. I guess you could parametrize them with time, right? Actually, that's probably just an objective improvement over my code. Generating these are a little slow. So there you go. If you want an improvement to this code and you want to make a pull request, by all means do it. Parametrize them by a time. So it would be one symbol, and then have the symbol values just be the times. That would be a huge improvement. In fact, I'm thinking about just pausing the recording right now and just doing that, but I am a little tired to do that. So I'll just leave it as it is for now because it's not that slow. And generating circuits, executing them is a little slower. And this would just make it so you don't have to, you just generate one circuit and then use a bunch of different symbol values. So I can't imagine that would be faster. I guess, I don't know, maybe it would be faster for I'm getting sidetracked. But anyway, then we have our trotter step. So we have a circuit that does the exponential where this is e to the negative I h bar, e to the negative I h t, where t is going to be our time. We have our Hamiltonian, which is a sum of terms, and we're approximating it by concatenating, which in a circuit is the same as multiplying these operations. So I here is our single component Hamiltonian term. Reversed simply is used for the Suzuki trotter where we want to reverse it instead of from I to n, from 0 to n, from n to 0. We have our simple Lie trotter where we just, for however many steps we want to do, we do a trotter step and divide by the number of repetitions. We have our base case for our recursive Suzuki trotter where we define our trotter step basically, and then we have a reverse trotter step And then we have our recursive definition here. So if our order is 2, of course the order has to be a multiple of 2 here. If our order is 2, then we just return our second order. Otherwise, define S sub k, create our first one, the first one in the equation, and then we repeat it twice because it's squared. Then do the middle one, which has this 1 minus 4sk term, then repeat the first one again. And so then we just, recursively will define this equation. So what we're going to be looking at here is several operators. We have our number of qubits being 4. Our qubits are defined here. This is the ZZZ expectation value. This is the sum of z's, which is, I believe, called the magnetization of the Ising model. I got that from a paper. That may or may not be the correct usage here, but I think that's what it is. We create our transverse field Ising model, define our time steps, create our circuits, and this is what would be improved, by the way, from replacing this. Rather than having t here be a number, have it be a parameter. That just gets passed. You wouldn't even pass it. It would just be a parameter here. But anyway, and then we create all of our circuits for large, medium, and small repetitions. 1 Trotter step, 3 Trotter steps, 10, and then Suzuki Trotter we have 1 repetition, but 2nd order and 6th order, and then we have 10 repetitions and 2nd order and 6th order for that. So here we're going to be looking at the ZZZ expectation values. So we can see the time evolution here. So this is Trotter 1 step, Trotter 3 step, Trotter 10 step. So increasing accuracy. You can see this is, you can't really see the blue. The blue overlaps extremely well with the purple here. That's why you can't see it. You can see though that the Suzuki Trotter with only 1 repetition, but 6th order aligns very closely with the 10-step Trotter. We can see further evaluation of these Suzuki Trotter evaluations here. So we have the 2nd order Suzuki Trotter. We have our 6th order, which is in green. And then we can see that 2nd order with how many repetitions? 10 repetitions is extremely close to the sorry, these were different colors, so I was throwing myself off, to the time evolution of the Trotter 10 step, which you can't even see because it's right aligns with, I believe, the red one, which is the the Suzuki Trotter 10 repetitions, 2nd order, or maybe it's the 6th order. But you can see that Suzuki Trotter allows for fewer repetitions. You'll have to actually investigate the number of gates. I don't remember how it scales exactly, but I encourage you to play around with this some more. And then we're going to play around with a little different model, and I like playing around with this one because it's Trotterization and quantum simulation. There's a lot of cool like graphs. Like normally graphs are just like lines, like a linear graph increasing, being like, wow, my fidelity is getting better, or my machine learning model is learning or something. Those are boring graphs. These are fun graphs, so that's what I like about it. And that, not gonna lie, that's part of why I did this, is for the fun graphs. So we have our product, the ZZZ operator. We have our magnetization, which is the sum of operators, and then we have our Hamiltonian, which we can also use as an operator, which will tell us the energy of the system. So once again, we create small, medium, and large Trotterization simulations. We can plot the following. So this is the ZZZ expectation value. You can see this is cool. Like look at this graph. That's a cool graph. Like look at those wavy lines. I can't complain with that graph. So you can see the T1 is blue, T3, which is 3 Trotter repetitions, is orange, and T10 is green. Now we're going to be looking at the magnetization. Once again, it's the same colors here. You can see similarity up to a certain time, but then 3 and 10 diverge. And then here we have the energy. You can see it has a very cyclic pattern to it, but it's just improving the estimations of it over time. So yeah, that's basically all I had for this in mind. Hopefully this was informative for some of you. It was a little longer than I was aiming for, but that's always what happens when I don't plan at all. And yeah, of course, code and relevant papers and resources for learning more will be available in the description. Though, I guess you can leave now. That's fine. No more trotterization after this point. The only thing after this point is talking about quantum machine learning. So leave now if you don't want to hear about it. If you do want to hear about it, the reason that I have not made a lot of quantum machine learning content recently is a lot of, I don't know, disillusionment maybe. I try to sort of look at papers and like see, it's somewhat, I don't want to say selfish, but the videos I make are a lot of times for me in the sense that, I want to, implement this paper or learn about this topic. So I'll just make a video about it and then I have to learn or implement it. So I implement the papers and I talk about the papers I think are relevant or fun or important or something to my own interests or, something like that. And recently I've seen a lot of papers on arXiv for QML and they're all the same. And they're all bad. And so I'm just like, I don't want to do any of these papers because I don't think any of them are good or interesting to me. I shouldn't be maybe that judgmental. So if you have a paper that you think is like, wow, this really it's cool, quantum machine learning, and feel free to share it below. And I'm very happy to take a look at it because I've seen so many bad papers, and this is true. I was a reviewer for NeurIPS, and so I did quantum papers there and some classical machine learning papers there, and it's just so many bad papers. So I'm very happy if anyone has papers that made them really excited about quantum machine learning. So yeah, that's it. If I find that paper, I'll talk about it and maybe it'll be more content. So that's it for now.